Okay, cool. Now it's recording. So please let me know if you have any question. So I always open the chat box so you can put it on the chat, or you can directly unmute your mic and say your question. Or if you want to say something, just say it or just put it on the chat box. Okay, so let's discuss about the solution here. So tutorial 3, distributed transaction management. And the question one. The question one is, let's say, consider we have the Olympic game database, and we have these two tables. This two table is just general tables. Let's say for the event table, so it has event ID and information about the event. So let's say in the Olympic Games, maybe it has running or swimming. So this event is about that. Like the event ID is one, and the event name is running, or and then the the more information about this event. And the second general table is athlete, and it consists of the competitor ID. So this table is about the athlete. So let's say maybe in this table they have the athlete name, address, and etc. Okay, and the important thing is here we have 5 more tables: result, medal tally, competitors, and medalists. So for the result, it consists of event ID, competitor ID, and position. And for the medal, it should be like, for the medal itself, it should be gold, silver, and bronze. And this one, medalist, the total medal won, and etc. Right? So the question is, when a race is running, a number of tables need to be updated. Assume that when an event is completed, a file is created at the venue giving competitor ID and position associated with the event ID. Then a series of transactions are executed which update other tables. And the question is, write a program to perform the updates using SQL insert into and update commands. Write the program as a single transaction bounded by begin transaction and commit or end transaction. So this question actually also related to your practical, maybe in the practical part 2, if I'm not mistaken. So the question, if you need to update some data in maybe three different user and different tables. So maybe we in the question you need to answer it using a single transaction, which is the query start with the begin and commit and end transaction, right? Okay, so before we see the query, before we see the answer, so there might be problems that occur because of this case. So what happened when two queries update the same data item? And then the second one is how to deal with the system failure. And the transaction is the square of read and write operation with computation step. And for the termination, we have a commit or we have abort. And this is the transaction property. So program mean a query. So this one, write a program. So this is the example, something like this. Program means query. Because in the question is, we need to insert a data. So here, when the race is running, a number of table needs to be updated. So after the event is complete, a file is created at the venue and then so we need to read the file and then insert it and update the tables. Nope, that is just so. If you learn about the SQL, actually in SQL we also have, we call it program. Like in the Oracle, if I'm not mistaken, we call it procedure. So we can create a procedure. We can even, it's look like similar to the code. So, but it's not another programming language. So it's just SQL. Okay. Okay, let's continue. This is the example of the SQL program, or we call it program. So we begin with the transaction and then begin transaction, begin input. We need the input, right? Because every event finish, it create a file. So that's why the input is the file, and then we try to read from the file and then update the table and also insert, right? So you have to pay attention with these 4 transaction property. I do believe that you you have got this material maybe from INFS 2200 or maybe from another database subject. So this is like general knowledge in database system. So in transaction, transaction has some properties. So the properties are atomic, all or nothing. So if we want to do like insert or update, so it should be atomic, all updated or nothing. So if we have distributed database system, we need this atomic one, right? So and then second one is consistency, the correctness from one valid state to another. Let's say if we have a distributed database system, so the cohort should be the replicas should be same as the master one, right? So if we have the mirror, or if we have the DB as the backup, with the backup DB on the replica should have same values with the master one. So that's why we call it consistency. And then isolation. So isolation cannot reveal its result to other before commitment. So maybe one of the example of the isolation is maybe let's say I have like 5 queries here. I have 5 queries, and then I make a program. This 5 query make to one query, right? Using begin and end, right? So if I execute this query, the result will be same or will be equal if I execute one by one in isolation. You got my point? So let's say this is like the first query, second query, third query, we executed one by one in isolation. And the result will be exactly the same. So that is isolation. Just a simple explanation. Okay, and the durability. Of course, we need this one. So after commitment, after we run commit, the result are permanent. Right? So this is the answer. Let's say we have this table. So this table is created. Sorry, this file, not this table. This file is created. This file is about the tennis man single. So we have 1, 2, 3, 4. 4 people. Andy Murray is the number 1, Julian is number 2, and etc. Right? So this is the answer. This is the program that you ask. So begin transaction, read input file, because every event finish, it generate a file. So read input file, if not empty, and then read input file, and then after read this one, let's say read the tennis Murray number 1. So we need to insert it, right? Insert into result, and then for the medals, for the medallists, so we have the condition here. So that's why we call it program, because even in SQL we can put a condition. So if the position is less than 4, because we need less than 4 because we only count 1, 2, and 3, right? So if position less than 4, let's say for the 1 we got gold, for the 2 we got silver, and else we got bronze, right? And then insert into medals and update, right? So this is just the example of the answer, right? So there are some issues here. I think I also mentioned it before in the previous slide. For the insert, we have two insert because we need to insert to the result table and insert to the medals, right? For the insert, it's okay. There is no problem. Really no problem. But for the update, we have a problem here. We need to pay attention with the update one. Why we need to pay attention with the update one? Because this one. So wait a second. Just ignore this one. This one is just about the primary key consistency, and etc. But this is not the main point of this slide. So please pay attention to number 2 and number 3. So here, let's say we're going to update medal tally. So medal tally consists of the country, medal, and number, right? Let's say the current situation, I mean the current table, USA have 10 golds, right? USA have 10 gold. And then we have a same event. Let's say the T1 is running. Let's say running, run, and then T2 is swimming, right? Okay, and somehow these two events, are start or in the same time, and the file is generated in the same time. And the problem is the USA got one gold in the running and also got one gold in the swimming. So USA got gold for the both event, for the running and swimming. So if we want to update this medal tally, first you need to read the n, right? So we need to read n, let's say because n is 10, and then we need to add one gold more. So we should write 11. And for the T2, because these two transactions happen in the same time, so T2 also read US has 10 gold. So because US won the swimming event and got one gold, so it should be at one more. So the result is 11. So both results are wrong because the result should be 12, right? Because USA got one running and one swimming, so it should be 12. So this is the problem in the update. So that's why we need to pay attention with this one. So the solution is we need log. So what is log? We will explain later here. So we have two types of log. The first is read log and the second is write log. So for the read log, it's not exclusive. I mean, like a single table can be read by multiple users or multiple programs. So read log is not exclusive, but write log is the exclusive one. So if the table or the data or the attribute or the item has been locked by a program, anyone else can write log that table. So this is the point. So write log is the exclusive one. And then we also have statement unlock. So after we use read log or write log, we should unlock. So the next slide, this is the answer of the 1-3. So here, so we should put write log in the table result, right? But this is not strictly necessary. The reason is why this is not strictly necessary, because in the table result and medal, we need to insert, right? So adding a new data, no problem. We have no problem with the adding a new data. The problem is when we want to update, right? So if we just adding the new data because the new data has no has no relation to any previous data, so that's why we have no problem with that. But for the update, because we need to know the previous situation, the previous data, so that's why we need to pay attention with the update. And then we need to update medal tally and medal list, so that's why here we should put write log, but this is not necessary at the table level. So that's why in here, so we have like this one. The notation should make clear the level of the granularity of the locking. So the level of granularity of the locking means this one. So you can lock the whole table or the only attributes, let's say the column, or the data items. So you can lock at the different level, right? So this one, read log table competitor, because we need to read. And then after you perform the transaction here, you need to unlock all the tables that you have locked before. And then don't forget to commit and transaction, right? Okay, and then, so how to do lock? How to lock? And then what is the rules of locking? So here we have two type of locks. Let's check. We have two type of locks. The first one is growing phase, and then the second one is shrinking phase. So this one is growing phase, and then this one is shrinking phase, right? So let's say I have this one is my first log, and then this one is the second log. And then the third one is the third log, right? So this is the transaction. So I do transaction here, I do transaction here, I do transaction here. So here I am in the growing phase. So the things that you need to pay attention is this one. When you release log, so let's say after the third log and then do transaction, I release log. When you release the log, you going to the shrinking phase. So after you release one log, it's mean you're going to the shrinking phase. You couldn't get any log more until you unlock all the log that you have. Okay, so when you release log, it's mean you go to shrinking phase and then you need to release all log. So this is the rules of two-phase locking. And this is the example of the deadlock and how we can solve the deadlock. Let's say we still have the middle tally and middle list because we need to update the middle tally and middle list. This one is the transaction 1, this one is transaction 2. Transaction 2 write lock the middle tally. And then transaction 2 also need to update the middle list, right? To update the middle list. But because middle list is locked by transaction 2, so that's why this one, transaction 1 is still waiting for the middle list available because a middle list is in the write lock transaction 2. And then here, the transaction 2 also want to update the middle tally. But to update middle tally, the log should be released for the middle tally table, and middle tally is locked by transaction 1. So that's why this one is waiting for middle tally. So in this situation, we got deadlock because transaction 1 is waiting for transaction 2, and transaction 2 is waiting for the transaction 1, right? So please note that two-phase locking can make sure our results are correct. This is a sufficient condition, but two-phase locking can trigger deadlock as well, right? And then one of the possible solution if something happen like this, the solution is we might just set the system timeout, because in this situation, the transaction will not going to happen because transaction 1 is still waiting transaction 2, transaction 2 is still waiting transaction 1, right? So it's mean deadlock. So if the transaction is not happen, maybe after 10 seconds or maybe after 1 second, maybe 10 seconds. If the transaction is not happen in 10 seconds, so we just we can set the system to abort it automatically or to timeout. So the transaction will be abort. So that is one of the possible solution for the deadlock. And the question 1, number 5, failure. Is there any condition in which the program would have to abort the transaction? Yes, of course. So we have some transaction failure here. The first one is incorrect input data. Let's say you have a table and you have a column that the data type is string, but your input is integer. So this is incorrect input data, right? And then present or potential deadlock. So if the deadlock, like in the previous slide, happened, and then we set the system, if transaction takes more than 10 seconds, it's automatically abort or it's timeout. So the transaction failure. And then data accessed by another transaction. So if the data is accessed by another transaction, or it's mean like write lock by another transaction, so it's my transaction might will not happen, right? So we should wait, or if it takes so long, it might be failure. And we also have the system failure, for example, media failure, processor failure, communication break. Let's say the site or the system is get offline, or maybe power outage. And our program Why we need database management system? Why we need a DBMS? Of course, for this error handling. Okay, and go to the next slide. The question 2, distributed replication. Okay, so let's say we have these 3 tables, middle, middle list, and middle tally. And we want to make a copy or make a replicas. We want to do replication here because we need to replicate it. If something happened to the master, so we still have the copy, right? And the replicas are located at different side, right? So clearly, the transaction in the previous question will comprise of set of sub-transactions executing at different side to the updating data there. The transaction can only finish when all its sub-transactions successfully finish. This process is enforced by using the two-phase commit to VC protocol. And this is the example 1. Let's say we have the coordinator here, and we have the site 1, site 2, and site 3. So this table are exactly same because it just replicas, just a copy, right? So here, so this is just a quick review, distributed data replication. I think you got this material from your lecture maybe. So the purpose of distributed data replication, of course, the system availability, the performance, right? So just imagine if you only have the single database and then you get multiple access, right? So maybe the bottleneck will happen, right? So if you only have the single database and then it's got multiple access, so it's maybe freezing or bottleneck. So that's why we need to mirroring, or we need to make a copy or replica. So instead of only accessing to one of the DB, the access can be distributed to replica as well. So that is for system availability and performance. And of course, scalability and application requirement. Replica should coverage the same values, yes. And we will have issue here, which is the consistency, right? So the idea is really ideal. Let's say we have the master data, and then we don't want to lose the master data if something happens. So that's why we do replication. We make a copy. We replicate it to many of copy or replicas. But the problem is the consistency, right? So we need to make sure, we need to ensure that all replicas are exactly same with the master one, or we call it consistent. And we have some question here, like where update are performed and how the update propagate. And we will discuss it in the next slide. So to do replication, to make a replica or to make a copy, we have 2 approaches. The first is synchronous replication, and then the second one is asynchronous replication. The synchronous replication is when the update commits, all the copy have the same value. So this synchronous replication has many benefits, right? Because it will ensure the consistency. So all replica must have the exactly same value with the master. And then no need for remote read, right? And then easy to handle failure, right? But it also has a drawbacks. The response time performance suffer from the slowest one. So let's say if we have this one, and then if we have multiple replication here, right? And then we want to replicate, if we give the update in this site, and then we want to replicate to all replicas. We want to update to all replicas, right? The point is all or nothing. So if we want to update, all replicas must be updated. If there is any problem in one replica, the update should be aborted. So all or nothing, right? So the problem is the response time. Let's say we want to update all the replicas, but one of the system are slow, so it also affect to another replicas. If any is unavailable, then the whole transaction cannot be commit or cannot be done because the concept is atomic, right? So the acid that I explained before in the previous slide, the transaction property. So you have to remember this one. So it's general knowledge, and usually we call it acid. Acid. Okay. Okay. And then this is the synchronous replica. We have a question here. Suppose there are large number of replica for metal tally, so we adopt the synchronous replica strategy for this table. So the benefit of synchronous replica is really good because if we have multiple replica, something like this, right? Because all of the replica are exactly same with another replica. So if we read this one, the value will exactly same with this one. So all the value in all replica are exactly same. So this is the benefit, right? So here, if you read this sentence, all the copy of the table should be consistent with each other at all time. The more side, the higher possibility of failure. Just imagine you want to make consistent to all replica and you have like 100 replica or maybe 1,000 replicas. So if one of the replica fails, so the update or the transaction must be aborted, right? So the possibility of failure is high if we have more side, right? And then if one of the replica side fail during the execution of transaction with update operation, the whole transaction need to be aborted. So this is the problem in synchronous replication. The second approach is asynchronous replication. So in this asynchronous replication, we introduce partially updated, or we introduce inconsistency. So we tolerate inconsistency for a better performance. So the example of synchronous and asynchronous will be in the end of this slide. So we will go there. So lower response time for update transaction, not all consistent, some replica might out of date. Because we call it partially update, so not all replica exactly same. Yeah, this one. This is the example. So that's why here we have different color here. This is the red one, but we also have the yellow one and the blue one. And this is blue or green, I don't know. This one. Okay, so that's why we have different colors, because the replica might have a different version. The value will be different, right? So would you recommend using asynchronous replication for this application? For the read is tolerable because you need to read multiple version, multiple replica to see which version that the latest one, right? And then for the update, we need strategy. So we will explain it more detail in the end of the slide, maybe the question, the question 4. Okay, we moving to the question 2 number, still question 2, number 3, distributed reliability. So we will have two-phase commit here, the example of two-phase commit. Suppose one of the metal tally replica site fails during the transaction. So the exchange of the message among sub-transaction resulting in the two-phase commit to issue an abort instruction. So you have to pay attention with the acid. So this one is atomicity and durability. All or nothing, commit, then permanent. All sides involved in this execution of the distributed transaction agree to commit before its effect are made permanent. And this is the example of distributed database structure. Here we have the master, or we have the coordinator, and we have a cohort, we have cohort, we have cohort, right? So, and this one, okay, so this is the two phase of commit. So we have two phase of commit here. So protocol, we have the protocol for communication. We have TCP/IP, HTTP, and SSH. You don't need to worry about this one because this is not related to our course, but just let you know that this is the protocol for communication. So if you do ping or if you just set up a network, you will see the TCP or IP, right? So this is like the protocol for communication. And HTTP is the port 80. If you're accessing web, so it uses HTTP. SSH is the secure of the secure one, usually port number 22. But don't worry much about this one. And then for the transaction, we use two-phase commit protocol. And what is the two-phase commit protocol? So we will explain it here in this slide. Okay, so this slide. So you have to pay attention with these two rules of the two-phase commit. We can call it two-phase commit or the voting phase. So coordinator asks cohort to prepare or to work. This one is like prepare message, prepare to update. The coordinator asks prepare to update to the cohort. Just remind you this is coordinator and this is the cohort. So send message, prepare to work or prepare to update, and then the cohort respond yes or no. Every cohort, let's say this one is first cohort, second cohort, and third cohort, every cohort does not know the situation of the whole transaction. So each cohort only knows about itself. Okay. And this is the important one. So that's why we put it on the red color. If respond yes, the cohort has to wait for the response from the coordinator. So even, okay, coordinator say, prepare to commit, and then the cohort said, okay, yes. But after that, this cohort cannot commit by itself. The cohort should wait the next instruction from the coordinator. So this is two-phase commit. So if respond yes, the cohort has to wait for the response from the coordinator. And then this is also additional important things here. Each cohort cannot abort by itself. So let's say the coordinator is failed because of the network or something. So this cohort cannot abort by itself. So it should wait from the coordinator. Okay. So this is two-phase commit. And this is the the commit phase. If all yes, ask cohort to commit, right? So the cohort send prepare message to all, sorry, the coordinator send prepare message to all cohorts, and then the cohorts say all yes, right? All yes, and then ask cohort, the coordinator will send message to the coordinator will send message to the cohort, commit to commit. But if one cohort say no, it should be aborted. Tell all cohort to abort. So only commit if all yes. And then after commit, after all cohort doing commit, the cohort will send acknowledge message to the coordinator. So this is the two-phase commit. And this is the example of the success scenario of the two-phase commit. Let's say this is the coordinator send prepare message or prepare to update to the all tables, to the 4 tables here. Prepare to update, and then got all yes. The coordinator got all yes response from the cohort. So this is from the cohort to the coordinator, all yes. So the cohort asks to commit to all tables. And then finally, after doing commit, all cohorts send acknowledge message to the coordinator. So this is the success scenario, right? And how about the failure? How if, so this is exactly same. The coordinator send prepare message to all cohort here, but the response from cohort, one respond yes, the second cohort respond yes, the third cohort respond yes, but the last cohort, the fourth cohort respond no. So what happened? So coordinator will send abort message to all cohort. This one. And then finally, after abort, all cohort will send acknowledge message to the coordinator. So this is the filer scenario. The filer scenario, right? So this is filer scenario in two-phase commit. So this is the another example in different figure. So let's say this is coordinator, and then send prepare, send prepare to. So the total cohort here is 4. So the coordinator send 4 cohorts to prepare to commit. And then the next slide, all cohort send, not all, so 3 cohorts send yes, right? 3 cohorts send yes, but 1 send no. So the result is all or nothing, right? So atomicity. If all yes, then do commit. If any no, just do abort. Okay. And yeah, this one, abort. So coordinator will send abort message to all cohort. And this one, final. So the all cohort will send acknowledge message to the coordinator. And this is the communication structure. This is exactly same, but in different figure, maybe to make you clear. So this is the coordinator, right? So coordinator will send prepare message to all participant, or we call it cohort here, okay, to all participant. And then the part, we call it fourth commit or fourth abort, because here some participant might be respond yes, maybe respond no, right? So if all yes, then coordinator will send commit message to all participant. If any no, the coordinator will send abort message to all participant, right? And then finally, the all participant or all cohort will send to the coordinator acknowledge message. Okay. So this is in different figure. And the question 3, number 2, two-phase commit filer handling. So, so we have different condition here. Let's say how if the cohort fail before receiving a prepare message. The second one, how if what if this cohort fail after receiving a prepare message but before making a decision? And then what if the coordinator fail before sending a prepare message? And then the last one, what if the coordinator fails after writing a board log record but before sending any further message to its subordinate? So here in two-phase commit, the coordinator has log mechanism. So the coordinator always write a log here to see the current state. So if something happen, let's say the site going offline, and then after the site back online, so it will check the log and then execute the uh, the queue task from the log. So this one, the first condition. This let's say this coordinator, and this is the one cohort. This is the first cohort. Let's say this first cohort, and others we have 3 different cohort here, right? The total cohort that we have is 4. So this is the second cohort. This is the third cohort. This is the fourth cohort. This is the first, right? So let's say the coordinator send to all cohorts, prepare to commit, prepare to update, right? And then this cohort, the coordinator couldn't send any prepare message to the first cohort, maybe because of offline, power outage, or internet problem, or etc. Because coordinator couldn't send any message to this one cohort, so the result will be abort, right? Even the others cohort respond yes, but we have nothing here, so that's why we send abort to all cohort. The second case, if the cohort fail after receiving a prepare message, right? So this coordinator send prepare message to all cohort. Everything is fine. Everything is working fine, right? Three cohort response, yes or no, maybe yes, let's say yes, but not, we got nothing from this first cohort. Maybe it's because of the trouble like power outage or the network offline. So the result is the coordinator will send abort message to all cohort. So the transaction will be aborted. And the third case is when the, oh, this one is still in the cohort after receiving a prepare message but before making decision, right? The situation is same above since the sub coordinator has not yet made a decision. No message has been sent to the coordinator. Yeah. And this one, coordinator fail. Let's say this one is when the coordinator fail. Yeah, of course. Since there is no prepare, commit, or abort log record, they can be unilaterally aborted and undone, and an end log record written. Since the coordinator didn't send the prepare message before it crashed, the sub coordinate or the cohort may abort once timeout. Right. So here they have a timeout system. Let's say after the 10 second, it should be timeout. Because the problem is in the coordinator, right? So this is the problem. And then the last one is also if the coordinator fail, but after sending the commit message, right? So this one coordinator send prepare, right? All prepare. And then, oh, we got nothing here. But finally, after after three cohorts say send respond back like yes, but the coordinator failed. So the happen here when the coordinator fail. So it's make a problem in two-phase commit, right? So the subcoordinate, so like the cohort cannot abort after voted yes, especially in this one, right? So if three voted yes here to the send yes to the coordinator, and then after that coordinator fail, so the problem is in two-phase commit, this cohort cannot do anything. So they just like a slave. They will do whatever the coordinator said. So that's why if the coordinator die, so this cohort cannot abort itself after say yes. So 2PC is blocking protocol. So that's why we have the 3PC. So 3PC, three-phase commit. So we will discuss it in the next slide. Sorry, okay. This one, three-phase commit. So what is different here? So in three-phase commit, each side use the write ahead log protocol. So all side, they have log protocol. So all message, all the condition, all state are stored in the log. So if something happen, let's say the site is being offline, the site is offline, and then if the site back online, so it can directly execute the all tasks that written in the log. And then set a timer for abort. So in three-phase commit, the cohort, if the coordinator fail, even the cohort say yes to the coordinator, and then after that coordinator fail, this cohort can abort by itself because already set timer for abort. So this is the two-phase commit. You can see the difference here. So in three-phase commit, we have pre-commit message here. Okay, so this one, maybe we can go to this example. If you want to further reading, you can go to this link. I will share this PowerPoint to you, I mean this slide to you. So this slide will be available after Friday afternoon, but if any student in my tutorial need this slide, I will send it to you. So non-blocking mechanism place the upper bound and the amount of time required before transaction either commit or abort. So this one in three phases commit, we also have the non-blocking mechanism, which is we set the timer for commit and for abort. So this is the example of the three-phase commit. So this is phase one, new in three-phase commit, and then the phase two, right? So if in the two-phase commit, we only have these two. But in the three-phase commit, we have the another one in the middle, which is the pre-commit. So let's say here, the coordinator will send a prepare message, can commit, and then the response, let's say the cohort said yes, right? So the commit is authorized. Okay, so if all say yes, it means that everyone is ready to commit, right? So everyone is ready to commit, and then the coordinator will send, okay, pre-commit, prepare to commit. So it's mean in this prepare to commit, everyone is ready for commit. So all cohort understand that another cohort are also ready for commit if all say yes for the pre-commit. And then after that, if all yes, and then do commit, and then acknowledge message have committed. So this is three-phase commit. Okay, any question? If no, we can move to the last question, which is question 4. Distributed data consistency. So this one is really interesting. So this one, we have distributed transaction management can cause primary copy-based approach or voting-based approach to maintain data consistency among multiple copies. So from my understanding, primary copy-based approach is like synchronous one, and this one is the asynchronous one. Because in voting-based, we can have a different version of the replicas. But in this primary copy-based, we just copy all the replicas. I mean, all replicas are copied from the master. So this is like, usually I call it like, this one is synchronous, synchronous replication, and this is asynchronous replication. So this is the example one for the primary copy. So primary copy is easy, like the ideal one. If we have this one is the master one, so let's say this is the middle tally table, and if we got the update here, this is the update, the yellow one, and then all replica should be updated directly, right? So all replica has the same copy, have the same values with the master one. Simple to update, primary set overload, primary copy, and then other temporary inconsistency. Okay, and then this is really similar to synchronous one. And this is the voting based one, which is quite similar with the asynchronous one. Okay, let's say this one, voting base. So here, we have the version number in each replica, right? So the advantage of this voting base or the asynchronous one is the more reliable, because if we see this one, let's say if we see this one, primary copy, this is the ideal one, right? We want this, right? We want, if one master is updated, all should be get updated. But this is reliable or not? The question is this reliable or not? So that is the question. Because if we have really huge number, let's say 1,000 of replicas, so we can say this is not reliable solution, right? But if we only have like 5 copies, that's still fine to use primary copy. So this one, the advantage is more reliable, and then write fewer copies, right? In the previous one, when master get update, all should be write update. All replicas should be write update. In this one, write fewer copies because each copy might has different version. So that's why write fewer compared to the primary one. And disadvantage, read transaction need to check money side because as I told you before that in this condition, one replica might has different version with the other replicas. The problem is if we only read one replica, we might get wrong because that replica might out of date and haven't updated yet. So that's why here we have the solution to guarantee can read the latest version. So how to do that? So let's say we have the n copies of, so we have the n replicas. Here n is equal to 4, right? N equal to 4, right? So we have 4 replicas, 1, 2, 3, 4, right? We have 4 replicas. So the important thing here is write at least m. So let's say we write m is 3 here. So we write version 0104. So this is m equal to 3, right? And then read at least n. So how many replica that should I read to get the latest version, to guarantee that I read the latest version? How many that should I read? The equation is this one. M plus n should be larger than the big N. So big N is 4, and then M, we just write 3, right? 3 plus, if we read 1, 3 plus 1, which is 4, 4 is not greater than 4. So let's say if we only read 1, we only read this one, we might get the correct version, the latest version. But what happens if we read this one? The version is 01, 03. So this is not the latest one. So that's why we couldn't read 1. If we read 1, there is no guarantee that we read the correct replica, that we read the latest version of the replica. So that's why the n, the minimum of n, minimum of the number replica that we should read is 2. So if 3 plus 2 should equal to 5, which is this 5 is greater than 4, right? 5 is greater than 4. So this satisfies this condition. So if we read 2, at least we can get the latest version. Let's say we can read this 2, or this 2, or this 2. So this is same. This is exactly same with this one. Just want to say, okay, if we write 3, so how many replica that should we read? So this is the point here. Okay, so this is the end of the slide. Hopefully everything is clear. So please let me know if you have any question. If student want to this slide, I can share it right now. So you can get this slide directly from me here. Can anyone confirm that you can open the slide? Okay. Yep. Is that correct slide? Wait a second. Correct slide, right? Yeah, okay. Okay, thank you for watching and see you next week. Or you have any question? Any student have any question? If no, we can end this session. No question? Okay, so we can end this session and see you next week. Thank you everyone for watching. I will end this session and bye-bye. Bye-bye everyone.